Hello. So far, we have seen quite a few languages to be not recursive, and we have also seen examples of languages which are not even recursively enumerable. Today, we will prove a very strong assertion about recursively enumerable languages, which will essentially I would say, establish that almost any question about Turing recognizable or RE languages are actually undecidable. And we will also see a subclass of Turing recognizable languages that are not even recursively enumerable. So these are two theorems from Rice, and we will one by one state and prove these two theorems. So they are actually very powerful theorems, and we will see that by no chance the languages that we have seen, like Turing machines with finite languages or I would say regular languages, recursive languages, these are all undecidable or non-recursive. So this is not exactly something happened by chance. It is actually the rule. Okay. Anyway, without further introduction, let me jump directly to the subject. Okay, so Rice's theorems. This is the topic of this lecture. In order to understand what it exactly means, we introduce a very important concept called properties of recursively enumerable languages. Okay, I will define this first. Before doing so, let me introduce this notation. RE, this is the class of all languages of Turing machines. Okay, for a reason I am not calling it exactly a set. This is actually beyond the scope of this, I would say, course, or beyond the scope of whatever is covered in your discrete mathematics course. Anyway, however, if, for example, you fix something like an binary alphabet for the input space of the Turing machine, then of course I can call it a set of RE languages. Okay, so it's a class of all RE languages that is called RE. Okay, so with the intuitive I would say understanding that RE languages are specified by Turing machines, this is basically a countable set, because every Turing machine can be counted in binary. Okay, can be I would say can be encoded in binary, and therefore as a finite binary string, and the number of strings over a fixed alphabet like 0, 1 is countable. So this is a countable set. Okay, provided that we restrict our attention to, let's say, binary encoding. Okay. Now, how do I specify a recursively enumerable language that is a member of this set RE? That is by a Turing machine. Okay. So a member of RE is typically specified by a Turing machine. But in general, if not always, this Turing machine is not necessarily unique. Any machine having the same language is a representative for that particular language in RE. Okay, but that is fine. I specify each member by some Turing machine whose language is equal to that member of this set RE. Okay. Of course, you have seen that there is something called unrestricted or type 0 grammars, which also specify recursively enumerable languages and are equivalent to Turing machines actually. So these unrestricted grammars can also be used to specify RE languages, but for convenience, we will represent RE languages by representative Turing machines. Okay. So with this in mind, I define a property of recursively enumerable sets as a map from this to the set true, false. Okay. So a property is essentially a subset of this RE. Those recursively enumerable languages that satisfy this property, okay, will be mapped to true. This T stands for true. And those that are outside that subset, they do not satisfy the property, and this P map sends them to F, false. So T is true, the property holds. F is false, the property does not hold. So in a sense, this property P is nothing but the membership function or characteristic function of this subset. Whatever it is, I will come to several examples to illustrate what I mean by this. So, for example, let's say something like this. Emptiness is a property. Okay. So define pemp, empty, to stand for empty. So it's a map from this to true, false, this set. So if L is empty, this is true. If L is non-empty, this is false. Okay. So how many properties is there? There are exactly as many subsets you have of this. Okay. So with respect to binary encoding, this is countable, but the number of subsets of this is uncountable. Okay. So that essentially indicates that I cannot specify most of the properties, but that's not exactly a very, I would say, important issue in this context. Okay. But the question is, how do I specify a property? After all, it is a subset and may consist of infinitely many recursively enumerable sets. Infinitely many recursively enumerable languages. Okay. And each such recursively enumerable language can be represented by multiple Turing machines. Okay. The idea is that we will choose any representative Turing machine of any representative element of any member of this P, okay, this subset, to represent this property. Okay, so that's the idea. So properties too are specified by Turing machines. So some Turing machine that has this property, that is some Turing machine whose language is empty, okay. And there will be many such Turing machine. We pick any such Turing machine as a representative of this emptiness property. Okay. So, yeah. So that's what is written here. The emptiness property is specified by any Turing machine M such that its language is empty. And I ask several questions when I am given a representative machine. What can I say about this subset, of which this M is a representative? Okay. So this kind of questions we will ask, and we will see more often than not, that is, except for only two exceptions, all such properties are undecidable. That is, if I give you a Turing machine M satisfying certain property like emptiness, and I would like to build a Turing machine, a total Turing machine, a decider, which will decide whether the given Turing machine has the property. Okay. And that problem is unsolvable. That is, no decider exists. But anyway, I will come to those formalisms little later. But let us first understand the definition of properties using some more examples. Okay. So here are some other examples. So emptiness property we have seen. So the finiteness property can be specified by any member of, that is, by any Turing machine whose language is finite. Okay. Likewise, you have, let's say, regularness property or regularity property. This can be specified by any Turing machine whose language is regular. It's not necessarily A star B star or B star A star, but by any Turing machine whose language is regular. Okay. Not a particular regular language, any regular language. Okay. So this is how this is specified. Likewise, the context-free or context-freeness property is specified by any Turing machine whose language is context-free. You can also talk about acceptance of a string. This is a property. So, if the string is something like 0, 1, 0, 1, 1, 0, 0, then this property is specified by any member or any Turing machine which accepts this language. Okay. And likewise, this is the fullness property. Like emptiness, this is fullness property. Any member of the set of all Turing machines or encodings of Turing machines such that the language of the machine is the entire sigma star. Okay. So, once again, we highlight that we specify a property, whether it is emptiness, finiteness, regularity, context-freeness, or whatever, by a single Turing machine whose language has that property. Okay. That is, the language of this machine belongs to that subset of RE. Okay. So, yeah. So that means we can definitely specify only countably many properties. But anyway, this is not exactly an issue of concern here. How many properties we can specify, how many we cannot. But with the understanding that those properties that are specified by single Turing machines, there are definitely countably infinite such properties. Most of these properties, except only two, as we will see, are undecidable. Okay. That is, given a member any property, something like you find out whether a given Turing machine has finite language or regular language or context-free language or contains 0, 1, 0, 1, 1, 0, 0, 0, or is the entire sigma star. All these properties are essentially undecidable. Okay. Okay, so yeah, this is once again some highlighting of the essential idea here. Properties are properties of recursively enumerable sets, not of individual Turing machines. In the next lecture, we will talk about properties of individual Turing machines, and okay, now depending on which property we are talking about, this Turing machine specific properties may or may not be decidable. We will look at it later. But for the moment, we will talk about properties of RE languages. Okay. And each property is specified by a single Turing machine, arbitrary. Okay. It's not a very specific Turing machine, but any arbitrary Turing machine having that property. That is, whose language is in that subset of capital RE. Okay. Yeah. So, a property must be independent of the representative machine. Okay. So, I hope you understand this issue. But in order to make the things clearer, I would also give you some properties which are properties of Turing machines but not of RE languages. Okay, so here are some non-examples of properties of RE languages. Okay, for example, the class of all Turing machines which has at least 2021 states. This is in general a property of M, that particular machine itself. Okay, but not of I would say the language it accepts. Okay, of course it can perhaps be proved that certain recursively enumerable languages require some Turing machines which will have to have at least 2021 states. This is similar to your DFA and all that kind of stuff. There may be some such results. I am not sure whether some such state-related results are available in the literature. But the idea is that whether a Turing machine has 2021 states or more or less, this is sometimes dependent upon the designer of the Turing machine. Here is an example. Consider a Turing machine whose language is the empty set. So they accept nothing. Okay. So you can definitely design M1 to have less than 2021 states. Actually, you can do it using only 3-4 states. Okay. Assuming that A, S, T and are 3 different states. Actually, you can manage with only just 3 states, S, T and R. So S is the start state. Reject state will be that state that immediately after the operation of the Turing machine. This is the okay. So in the very I would say very first step of the transition itself, it moves from state S to reject R. Okay, so this will be, and that T state will also be there because by definition it has to be there, but it is unreachable. Okay. So you can definitely design M1 as a machine with as few as 3 states. Okay. So I can also design a Turing machine with more than or at least 2021 states. For example, I am eventually going to I would say reject everything. Okay, so I can do something like that from start state, which I may call P0. From this, I will just go to P1, then to P2, then to P3, and so on, and maybe P2020. So this already accounts for 2021 states, and after that I will jump to the reject state. That is possible, right? Every time I move right, switching to a different state. After 2021 such states, I will just go to reject. It's a delayed decision, but this illustrates that how many states M would have is often the choice of the designer of the Turing machine. In some case, it may be less than 2021. In some case, it may be 2021 or even more. Okay. Now, this is not a property of RE sets or RE languages. The reason is that, of course, this is not a property of this empty phi, because if I use M1 as the representative Turing machine, then this property is false because it has less than 2021 states. On the other hand, if I want to represent phi, an empty set, by M2, then this property is true. Okay. So depending upon the representative Turing machine, this assertion is true or false even when the languages of the two Turing machines are the same. Okay. So essentially, having 2021 or more states is often associated with the design of the Turing machine. It is not associated with the language of the Turing machine. So this is a property of Turing machines, not of RE languages. Okay. So let us see some other examples. Any member of something like M, such that M is a total Turing machine. Okay, this is again totalness is often a choice of the Turing machine. If you take a recursive language, then there exists a Turing machine which halts on all inputs, but you can simply tweak that Turing machine so that you have a new reject state R prime, that whenever you enter R, you enter an infinite loop there and you never go to R prime. Okay. So the language of the Turing machines remains the same, but one is total, the other is not total. Okay, so being total is sometimes a choice of Turing machine, but of course if M is not recursive, then it cannot have, or the language of the Turing machine is not recursive, then it cannot have a total Turing machine. And in that case, this is not exactly the designer's choice, but if the language of M is recursive, then this would be the designer's choice. Okay, so this is a property. Being total is often, not necessarily always, a property of the Turing machine, but not of its language. Okay, so here are some other examples. Any member of this, that it rejects this and halts. Okay, the idea is that it may also loop when the input is this, and in both cases, this is not accepted. So this is often a property of M. Okay, not the language of M. And here also it looks like a property of Turing machines only. M ever goes to the right of the input. Okay, this is actually a property of the machine itself. There exist languages for which this may be the case. For one Turing machine accepting that language, and not the case for another Turing machine accepting exactly the same language. So this is a property of Turing machines, not of their languages. And here is yet another example. Any member of M such that M has the least number of states among all machines accepting L of M. Okay. So again, like I would say, the minimum DFA, you can, I would say, construct Turing machines with the least number of states, but they are not same. Okay. Anyway, so these are properties of Turing machines, not of their languages. Okay. So we will concentrate upon only the properties of RE languages. Okay. And we will see that most of the questions that we can raise about such properties are undecidable. Some are even semi-decidable, non-semi-decidable. Okay, so let us see. Okay, so to that effect, I need to introduce two types of properties. Okay, one is called a trivial property, other is called a monotone property. Okay, a property is called trivial. Recall that a property is defined by a map P from the set or class of RE languages to true or false. Okay. There are only two properties that are trivial. That is the constant map that takes every RE language to T, and the constant map F that takes every RE language to F. Okay, so these are the constant map. So this is the true map. Okay, so this is the entire RE. Okay, and this is another constant map. So this as a subset, this is the null set. Okay, so this property is called trivial because it trivially holds for all RE sets, and this is also called trivial because it trivially does not hold for all RE sets. And any other property which for some languages the image is T, and for some other languages the image is F. That is called a non-trivial property. Okay, any other property is called non-trivial. For example, this is a trivial property. LM is recursively enumerable. Because given a Turing machine, its language is definitely recursively enumerable. In fact, this is how recursive enumerability has been defined. Okay, so this is true for any Turing machine. So this is a trivial property. Trivially true property, to be more precise. And this is the non-trivial property. The language of M is recursive, because we know that there are Turing machines which are recursive, or whose languages are recursive, which are total Turing machines, and their languages are recursive. And there are Turing machines, there are recursively enumerable languages which are not recursive. Okay, so if M is any such machine, the language of M is not in this set. Whereas if I take a recursively, if total Turing machine, its language is recursive. So it's not universally true or universally false. So this is called a trivial, non-trivial property. Okay. The second property that we will use is called monotonicity. So we assume that false is less than equal to T. So this is not a very bad thing. For example, in the binary world, the digital world, I can represent fault by 0. That's a common thing. And I can represent true by 1. So 0 is less than equal to 1. And then the definition says that whenever A is a subset of B, or in other words, whenever B is a superset of A, the property P of B must be greater than equal to P of A. In other words, T is 1, this is 0. Okay. If for some subset A, okay, for some RE subset A, this property is already true, it has to be true for all RE languages which are supersets of A. Okay, so A is an RE language, B is an RE language. If it is true for A, then take any superset of A, the language has to be true. So T less than equal to F in this context is not allowed. Okay, so that is called monotonicity. So here are a couple of examples. Infiniteness is a monotone property because if this is an infinite set and we have a superset of it, it also has to be infinite. Okay. Likewise, if I consider if A is already sigma star, then any superset will have to be sigma star because everything is contained in sigma star. Okay. So these are monotone properties. On the other hand, if I consider that other things, LM is finite. Okay. This is not a monotone property, in which case we call it a non-monotone property. Why? For example, the empty set is finite. Okay. So property P of empty set is true. On the other hand, if I take sigma star, which is an infinite set, definitely empty set is contained in sigma star, but P of sigma star is false. And this will say that true less than equal to false. This should never happen. Okay. And like sigma star, you can also have phi. So these are non-monotone properties. Okay. So we'll use these two types of properties in the two parts of Rice's theorem. So we'll start with trivial properties. Okay. So that is Rice's theorem part 1. It says that any non-trivial property of recursively enumerable languages is undecidable. Any. This is very, very important thing. Not some. All non-trivial properties. That is, except for the two trivial properties which trivially true or trivially false. Any other property is undecidable. What does it mean? This essentially means the set of all Turing machines n, or for that matter set of the encodings of all Turing machines n for which the language satisfies this property is not recursive. Okay. So this is a language, right? The encoding of all Turing machines whose languages do satisfy the property P. This is not a recursive language. Okay. So how do I prove that? So this proof is not really very difficult. Okay. And given that we have seen several examples of, I would say, reductions to prove undecidability or non-recursiveness of languages, this is not exactly a very difficult thing to prove. Okay, so let us now start with the definition. So let's say P is a non-trivial property. I have to show this language is not recursive. Okay, so we'll have a reduction from a non-recursive language to pi. Okay, and we will actually have a reduction from the halting problem to pi. Okay, now for the moment, suppose that the property is not satisfied the empty set. Okay, what will happen if it is satisfied? I will just mention it a little later. For the moment, let us say that the property is not satisfied by empty set, like non-emptiness property or infiniteness property, something like that. Okay, it's not satisfied by the empty set. But this is a non-trivial property, so there must exist some recursively enumerable set L for which this property is true. It is not universally false, so it must be true for some L. Okay. So since P is non-trivial, there must exist a recursively enumerable language L, and of course, it cannot be empty, it is non-empty, such that the property is true for this L. And since L is a recursively enumerable language, it is accepted by some Turing machine, and let us call it K. Okay. Let K be any Turing machine whose language is equal to this L. Okay. With this in mind, we will propose a reduction from the halting problem to this HP to pi. Okay. And this is actually a reduction from HP to pi. And the same reduction will work if this is true. But then, since this is not universally true, I will have some L in RE for which P of L is false. And we will take a Turing machine such that the language of K is equal to L. The same reduction will work. Only thing is that the reduction will be from the complement of HP to. Okay. The reduction will be complement of HP to this pi. But this is not a very, I would say, bad thing, because HP is not recursive. HP complement is not recursive also. Okay, because recursive languages are closed under complementation. In fact, in this case, this property is not even recursively enumerable because the complement of HP is not even recursively enumerable. Anyway, that's not important issue here, because in this part of the theorem, I am talking about recursive, non-recursiveness, not non-recursive enumerability. Okay, non-REness. Okay, so we are talking about non-recursiveness. In particular, we know HP complement is also not recursive. So this will prove that pi is not recursive. Okay, so this reduction is not very alien. You have seen similar things. So the reduction engine, what are the inputs of this reduction engine? It's an instance of HP, if this is the case, or HP complement, if this is the case. Okay. In each case, it is M hash X. Okay. And the question is whether M halts on X or not. Or if it is this case, whether M does not halt on X or not, or it does. Okay. So input is m hash x, and as an output, this reduction algorithm will generate a single Turing machine n for which the property is true if and only if m halts on x. So I am looking at this. Okay. This one will work in an exactly parallel way. So let us concentrate on this case. P phi equal to property if the empty set does not satisfy the property. Okay. So and this reduction engine can actually embed the notion of m, x, and also this Turing machine k in the finite control of n. We have seen this is not a difficult problem. Only thing I have to mention, as I mentioned in the earlier lecture, or maybe the earlier 2 lectures, I have to specify the main function for n, how it will behave. Okay. So as you understand, it will simulate m on x and k on something. Okay. Anyway, let's see this. You have actually seen this. Okay. This kind of reduction earlier. So input is an instance of the halting problem, and the question is whether m halts on w. I will prepare a machine n. This is the output, a Turing machine n, because we know that we will specify a property by a Turing machine which has this property, as that n has this property if and only if m halts on w. Okay. So this is how it goes. So I am essentially writing, so I am not specifying those things how the reduction engine embeds the information of m, x, and k. This is essentially a set of copying. Okay. And it can be a copy to the finite control. It can also be a copy to the tape, whatever it is, some read-only tape, doesn't matter. So this is the main function for n. Okay. So copy v. Okay. So n has so this w is an input for m. And I am preparing a single Turing machine n which has an independent input v. Okay. So for the moment, store v in a separate tape or track, whatever. Okay. First, you simulate that m on w. So you can copy w from the finite control to the first tape and simulate m. For that matter, if necessary, you can copy the description of m from the finite control to a second tape, second essentially read-only tape, after copying its read-only. Anyway, so you first simulate m on w. Okay. If the simulation does not halt, then the next step will not be executed. But if the simulation halts, then you come back to v. So once again, you copy back v to the first step or whatever, wherever you simulate k on v, and accept if and only if k accepts. Okay, accept if and only if k accepts v. So accept what? Accept v if and only if k accepts v. Okay. So now let us see. Okay. So this conversion from m hash w with a constant knowledge of k can be done by a Turing machine. This is which is the reduction algorithm. And this is the main function for n. Okay. And now I have to show that this condition is satisfied by this reduction algorithm. Why? If m halts on a, then n will eventually come to this third step and simulate k on v. Okay. And it will accept if and only if k accepts v. So in this case, the language of n is nothing but the language of k, which is L. And by the choice of L, the property is satisfied by L. On the other hand, if M does not halt on W, then what does it mean? It means that M loops on W, which means this simulation of step 2 will never end. Okay. Therefore, this N will get no chance to come here and accept anything, irrespective of whether K accepts V or not. Okay. It will be simply stuck in this second step. Okay. So in that case, the language of N will be empty. And we have seen that L satisfies the property, whereas the empty set does not satisfy the property. Okay. So once again you see, if this is F, this is true, then we have chosen L such that this is F. Therefore, this is also a valid reduction, only it's not a reduction from HP, it's a reduction from HP complement. Okay. So, that establishes that any non-trivial property, again let me highlight, any non-trivial property of recursively enumerable languages or RE sets is undecidable. Okay. Finiteness, that includes finiteness, context freeness, recursiveness, all these things are undecidable. Okay. Yeah. So a very strong statement, a very strong, I would say, assertion about the ability of total Turing machines. They are almost worth, in a sense, nothing. Anyway, so Rice's theorem part 2 is the second part, which talks about monotonicity. Recall that a property is called monotone if it is satisfied by some recursively enumerable language. Okay, whenever it is satisfied by some recursively enumerable language, it has to be satisfied by any superset of that recursively enumerable language, which is itself a recursively enumerable language. Okay. So, like non-trivial, I will now consider non-monotone properties. And the part 2 of Rice's theorem says that any non-trivial property is not recursively, is unsemi-decidable. That is, no non-monotone property P of RE languages is semi-decidable. In other words, the set N such that okay, so maybe I write it a little bit more than this. If P is a non-monotone property. Okay, for any non-monotone property P, set of all Turing machines or set of the encodings of Turing machines, the language of all encodings of Turing machines, whose languages satisfy this property, is not only not recursive, it is not even recursively enumerable. Okay. So this reduction, this proof involves a reduction slightly more complicated than the previous reduction. But let us look at it. Okay, so let P be a property which is not monotone. Okay, and since this is not monotone, there must exist recursively enumerable languages L1 and L2 such that L2 is a superset of L1. For L1 this is true, this property is true, whereas for L2 this property is false. That is what non-monotonicity will imply by definition. Okay. So there must exist languages L1 and L2 such that L1 is a subset of L2 or L2 is a superset of L1. The property is satisfied by L1 but not by L2. Okay. So you fix any two such languages L1 and L2, and since these are RE languages, you will have some Turing machines K1 accepting L1 and some Turing machine K2 accepting L2. So you pick any such Turing machines K1 and K2. Okay, so take any Turing machines K1, K2, such that the language of K1 is this L1 and the language of K2 is this L2. Okay. And now, since this is a non-addiness proof, a reduction from HP will not do. So I will make a reduction from the complement of HP, which is known to be not recursively enumerable, to this language pi. Okay. So once again, the reduction algorithm takes an input and instance for the complement of HP, which is AM hash W. So it will embed the knowledge of AM and W in the finite control of the representative Turing machine N that will be output by the reduction algorithm. Moreover, it will embed the knowledge of K1 and K2. These are two constant machines depending upon the choice of L1 and L2. Okay. So the reduction algorithm will also embed the knowledge of K1 and K2 in the finite control of the output machine N. Okay. So I have to specify the behavior of N, which is basically the main function of N, in order to complete the description of the reduction algorithm. Okay. So it will embed the information M, W, K1 and K2 in the finite control of N, the output machine. Okay. So the input is M hash W, output is a Turing machine N, such that the language of N satisfies the property if and only if M does not halt on W, because it's a reduction from the complement of HP to pi. So does not halt means the property holds. Halts means property does not halt. Okay, that is false. True if does not halt, false if halts. Okay. So this is the main function for N. So it will run actually 3 simulations. M on W. Of course, now W is an input for M, whereas N has a private input V. So it will run 3 simulations in parallel. Okay, parallel means in time sharing fashion. M on W, K1 on V, and K2 on V. Okay, so I can assume that we have sufficiently many steps so that 3 simulations can run in parallel. And parallel running means do one simulation of one step of M on W, one step of K1 on V, one step of K2 on V, then go once again do one step of M on W, K1 on V, K2 on V, come back to M. So this way, in a time sharing fashion, it can run 3 simulations in parallel. Okay. So copy V from the first step, W from the finite control. Okay. So you need to simulate two instances of 2 simulations on V and 1 simulation on W. So you may copy V to 2 taps and W to 1 tap and run 3 simulations in parallel. That is 1 step of each in round robin fashion. That is M, K1, K2, M, K1, K2, M, K1, K2. Okay. So that every machine gets the chance to accept or reject by halting eventually, if it does so. Okay. So K1 on V on first step, K2 on V on the second step, M on W on the third step. Okay. So 3 simulations are running in parallel in a round robin fashion. One on this, one on this, one on this. Then go back, 1 step of this, 1 step of this, then 1 step of this. And when will N accept? If and only if one of these 2 conditions holds. Okay. Accept if and only if one of the following conditions hold. Actually, there are 2 conditions. One, K1 accepts V. Okay. K1 accepts V. Then independent irrespective of what K2 or M, this simulation or this simulation they are doing, accept. The second condition is K1 may fail to accept, but if M halts on W, simulation on the third step halts, then accept if and only if K2 halts on, not only halts in the accepting configuration on V, this simulation. Okay, so this can be done by N, right? Given that it can perfectly simulate M on W, K1 on V, and K2 on V. Okay. So now let us see what is the language accepted by this output Turing machine N in the two cases when M does not halt on W and M does halt on W. Okay. So first, suppose that M does not halt on W. Then there is no way this condition 2 is true. Okay. If M does not halt on W, then the simulation on the second step of K2 on V does not matter because this condition is never satisfied. Okay. So in that case, N accepts V if and only if this simulation accepts V. Okay, condition 1 holds. And therefore, so this 1 is the only way it can accept V. Okay, because this condition is never true. So, N accepts by criterion 1 only. And therefore, the language of N is exactly the same as the language of K1, which is equal to L1. And you recall that L1 does not satisfy the property. Okay. No, L1 does satisfy the property. Okay, so that's the choice. L1 satisfies the property. Yeah, L1 satisfies the property. L2 does not satisfy the property. Okay. So in this case, property of L of N is true. Okay. On the other hand, if M halts on W, then N accepts V if and only if either K1 accepts V or K2 accepts V. Because this is going to halt eventually, and all the three simulations are running in parallel in a sense. So if either this condition holds or this condition holds, then N is going to accept. Okay. So in this case, the language of N will be the union of the language accepted by K1 and the language accepted by K2, which is L1 union L2, but we have seen that L1 is a subset of L2, so it has to be L2. Okay. So if M halts on W, N accepts if either K1 or K2 accepts V, and in this case, language accepted by N is nothing but the languages accepted by K1 in this simulation or the language accepted by K2 in this simulation. So it is this union this, which is L1 union L2, but L1 is a subset of L2, so this union is nothing but L2. So in this case, property, okay, maybe I do not use this. In this case, P of the language of N is false. And again, let me write, in this case, P of language of N, which is L1, this is true. Right. So, the property is true if and only if M does not halt. Okay. So, M does not halt, property is true. And if M halts, property is false. Therefore, if P is a non-monotone property, then this reduction establishes that the corresponding language pi has to be non-monotone. RE. Okay. So these two are actually quite, I would say, powerful theorems about RE languages. Of course, in this case, I would say it's not like almost everything, because almost everything I can talk about when I talk about non-trivial. Okay, but non-monotone is not, I would say, that common. But despite that, we will see that there are many examples. For example, you can see that this fin property, is it monotone? No, it is not monotone. Okay. Because if some, for finite sets this is true, and for infinite supersets this is false. So this will say the property of finiteness, okay, is not semi-decidable. But the complement of this does not directly follow from Rice's theorem. But anyway, it's okay. And despite that, I would say that Rice's theorem part 2 is yet another very, I would say, deep and intriguing result about the properties or about Turing machines. Okay, so with these two deductions, we will stop for today. So here are some tutorial exercises. I think this part A is not correct. Yeah, because infiniteness is a monotone property, so you cannot use. So yeah, so this was raised by somebody in the last year also. So I will just update this. So this is not true, but this and this is true. And yeah, so this is Rice's theorem part 2, non-RE. And here are some other interesting examples, some properties of a pair of RE languages, which essentially indicates things like this. Given to Turing machines, decide whether the language of M is equal to the language of N, or contained in the language of M, or are disjoint with each other, and similar things. Okay, so these are all undecidable properties. Okay. Anyway, we will solve a few exercises of this kind in the tutorial session. Fine, so that's about Rice's theorem. These two theorems are pretty powerful, and yeah, but this is reality. We have to accept. Anyway, see you in the next lecture, when I will actually talk a little bit about properties of Turing machines rather than properties of RE languages, that is, their languages. Anyway, bye for now.